Okay. Okay, let me start from the beginning. So, okay. So I would like to talk. Yeah.
So
maybe. Yeah.
Introductions. So I think you've met everybody except maybe Matt. Have you met Matt?
Hello.
Hi.
Okay, so you guys get. Okay, good. And so we're very pleased to have Sara visiting us, and this will actually be, hopefully, she's already had some one-on-one meetings. She's here again until tomorrow. I think there's a bunch of like discussions to have pairwise and triple-wise, and maybe over lunch we can brainstorm about some of those. One of the ones in particular will be tomorrow's meeting at 1 o'clock, which will be going over the PSL journal article. But then another one is, and make sure I have this right, next Friday at 1 o'clock, Hugh is going to present the ADMM.
We need to talk about the timing for that because I think he's flying that day. So either we could do it at 11 a.m. that day, or we could push it back.
And we may want to coordinate with Sara. You'll be back in EU by then,
Mm-hmm.
so that may push the time earlier to make it potentially feasible.
I'm usually a night owl, so it doesn't. Usually,
okay.
Unless you do it, at 3 in the morning for me, then I should be fine.
Okay, then that's really good because that will make things much easier. But anyway, so we'll try and have a meeting next week that will talk in more detail even about some of the things that we're doing with ADMM and hopefully connections to things that Sara is doing. And then maybe we'll also have some follow-up meetings about causality because I think you guys could all tell I'm all excited about causality after having come back from this colloquium on causality. They just actually posted the videos from that, so we may even want to pick out a few of those and watch the videos together. So, but now let me hand it over to Sara.
Okay, so I will speak about FoxPSL, which is essentially another implementation of PSL. And then I will speak shortly about how we try to use FoxPSL with causality. So we try to do causal discovery and we try to use FoxPSL. And that's very much in progress, so I will just sketch what we did and then I'm very curious about your comments. So this is joint work with several people in Switzerland and Amsterdam. And
And let's do a sound check. So everybody on the East Coast can hear us okay?
Yep.
Yeah.
Okay.
Yeah,
You can.
yeah, it's really nice, right? Okay.
All
right. Okay, so what is FoxPSL? Well, it's a distributed implementation of PSL. It's based on a distributed graph processing system called Signal Collect. So I know that Hugh was working on a distributed version in GraphLab. This is another distributed graph processing system in the same family. And we call it FoxPSL essentially because I like foxes. But then we backronym it and we say, okay, it's fast because at least in our experiments, our implementation beats the old version that Hugh did. It's optimized because it has some optimizations, and it's extended because we added some extensions to PSL for the things that we want to do. So these extensions are mostly about, we have a class system, so it's somehow similar to what PSL does, but also somehow different. So we can see this actually in the next slides. So mine, yours, let's do this. Much happier. Okay. So first I will say what Signal Collect. So Signal Collect is a project from the University of Zurich, and it's, as I mentioned, is similar to GraphLab, Fraggle, or other distributed graph processing frameworks. And it's called Signal Collect because you have nodes. These nodes, they send signals, so they signal, and then they collect. It's and not a fantasy.
But if you contrast, you guys probably know more about all these distributed settings, but so the various gather, the various different paradigms. How does it
So this one is supposed to be faster, at least in the last journal we published, which was 2 months ago. We have this is a comparison of signal electric power graph, which is as far as I understand an evolution of Kepler. So in this case it is the time, this is the execution time, and the signal electric is 3 times later.
I'm having a lot of trouble hearing this discussion. I imagine other people are too.
So is the reason that you're not hearing the discussion is you can hear Sarah, but you can't hear me?
I think Sarah must have turned away from the mic because it's hard to hear her as well.
Okay, can you hear her now?
Hey, can you hear me? Everything fine?
When you asked that question, I could hear you really well, Lisa, but I couldn't hear Sarah well.
Okay, so because I was turning around to the screen. Maybe I should turn. I'll try to speak into the table somewhere. Let's try this.
Yeah, and so my question was, again, just very basic, of the various distributed graph paradigms, and maybe Hugh can answer this. So, you know, there's the vertex programming flavored ones, there's the kind of map reduced flavored ones.
This is the vertex one.
Okay, and for the vertex one, how does is there some key difference between this vertex programming abstraction and what was it? Well, the gas one, the gather.
And that's a paradigm, right? So like most of them sort of subscribe to the paradigm of the gather, the applying, and the static phase. So in general, that's the paradigm. This is an implementation.
Okay, so there's nothing different about this vertex programming paradigm than any other vertex.
The implementation is different. So like the graph has this same memory, and this one sends messages. So how, in theory, you can write the same programs. That's why they compare. But in practice, the results may be different. So they claim in the last journal, and usually tell them, because I work with that, that they are for simple algorithms like Persian, the filter, and the
Hey guys, the sound has not improved. Are you using some sort of are you using multiple mics or something? What's going on? Like it sounds like there's a cable loose.
Like me, like this. Let's try this.
Oh, that sounds great. What'd you do?
Apparently, the Mac has a microphone on the left side, not in the center. I was trying to speak to the center.
No, speak on this side. It's good side.
Well, so now you know for the next time.
All right, so my question is about the different implementations of the vertex programming and the fact that I just want to understand the difference in the implementation for the signal collect one that you're using versus the graph lab one.
So the graph lab, for example, has this shared memory. Yeah. So they write like the process is connected to shared memory, and this one is like different messages. So for different algorithms, one or the other might be beneficial. Okay. And in general, for example, for the patient, apparently it's beneficial to have signal collect. So that's what we show. And so our implementation has some optimization, so it's a bit difficult to factor exactly why, but also our implementation is faster than the 3D like 1 minute. So we can it's a bit difficult to factor because we change the system. But we can discuss later. Okay. So besides the fact that it's faster with contingent, we also have several other things. They allow us synchronous execution, which for example Peggle doesn't. We can decide between synchronous or synchronous. It's very extensive and pseudo. And we can also have an incremental mode, which means that you can add nodes at runtime if you complete stuff. But we didn't make use of that. There are few stuff that my interest will be interesting for that. So this is the architecture of FoxPSL, which is essentially the architecture of every PSL implementation, or most of them, I guess. So we have a problem. We describe it in FoxPSL language, inventing the domain specific language. you do the grounding, then you take the grounded rules, you convert everything to a complex minimization problem, and then you solve it, for example, with the ADMM processor optimization. And we implemented the ADMM processor optimization in signal collect. The rest is outside.
So we're again having a little bit difficulty hearing you. So
It's really funny. Yes, only to the idea. Maybe sit to this in fact. We'll talk to the mic. Okay, so what I was saying is that we implemented the DMM in Sigma Collect. Sigma Collect can run on local machine and it can run on the cluster, and I think that's the same for all of this distributed processing system. No. Okay. I'm Italian, I cannot speak.
No, it's fine. Speak.
Okay. Okay, so I'll try again. So essentially, well, this is nothing special. Just the difference is that we use Sigma Collect, and instead of using Java, we use Scala, but that's essentially minor differences. And the good thing is that Scala and Java, they both run on the JVM, so you can actually essentially mix the two.
Okay. And how was that? Could you guys hear her?
Can you hear me?
yeah.
You can hear you better now.
Better. Okay. Okay, I keep trying to talk. I feel it's safe, but I'll try. Okay. So first I wanted to say why we call it extended. So this is essentially it's our take on how we would like PSL, how we would like to write PSL programs. So we have some classes. So for example, we have the class person, unnumbered by people. We have the class party. Democrats and Republicans are parties. And we can have also individuals which don't have a class. So UFO doesn't have a class. And then you can describe the predicates. And the predicates, for example, something is retired, and anything can be retired. Or you have a predicate teaches, where a professor. I lost them. Hey.
Oh.
Okay. Okay. I was hearing the white noise and suddenly no white noise. So.
Someone muted their mic.
Okay, good, good. So essentially, you have teachers, you have a professor teaches a course, and they teach this course to a student. And so this is, I'm sure it's very similar. Markov logic has this, I know other logics have this. So what we try to do, we also try to infer automatically the type of the individuals if you put them in some facts or in some rules. Let's say if you say that Anna votes Republicans, you don't need to say that Anna is a person and Republicans is a party, because you can infer it automatically, knowing that voting is a thing between a person and a party. So that's essentially the things we added. So then you can define constraints. This is the same as PSL, it's just the syntax is different. So when we define the predicate friends between people, we attach the constraint already to the predicate. So we say that the friends is symmetric, means that if Anna is friends with Bob, then Bob is friends with Anna. That's symmetric. We have also functional and partial functional, so the things that already PSL has, but the syntax is slightly different, so we add it already to the predicate, and it's not a constraint outside. Then we describe the facts. So we can describe that Anna and Bob are friends, and we say that the truth value that they're friends is 0.8. So this is all just a different notation for the same concepts that you already know. And then we can describe the rules. So this is one of the rules from the data set of voters. So if somebody votes a party and another person is friends with this person, they're more likely to vote the same party. So this is all very simple. We can add also, I'm not sure actually if you can do it in PSL for each rule. We thought it was possible, so we just added each rule can be linear or square. You can decide for each rule. And you can have these things we call partially grounded rules, which they might be also in PSL, but I haven't found them described. Essentially what you do is you can have a mix variables and individuals in the rule. So the rule is, some part of the rule is grounded. So this one says if somebody is rich, then it's more likely that they vote Republicans. So, no offense to anyone.
You can do it in PSL, but it's not well documented.
Yeah, exactly. So I was not sure if it was there or not. So
Yeah,
it seems like a
it's there.
trivial
It's
thing.
there.
Yeah. Okay. So then we tried to add this existential quantifier, which I know we discussed. So so the problem is with the existential quantifier that, as far as I know, in none of these logics, Markov logic or PSL, there is no way to do Skolemization. So the only way you can do the existential quantifier is you unroll it in this junction, which becomes huge. So what we tried is we tried to say, okay, but at least if we have the classes, then we can do it on a partition. So that's the only way we thought we could solve it.
Yeah, and we have some work, which I know they can't hear me say this, so, but we have some work that is looking at specific ways of doing existentials, but actually we haven't got them working yet. So for the rest of you guys to know that Alex in particular has done some work on a very specific case of needing to do this.
Okay. Yeah, so I was not aware of any way, and I couldn't think of a trivial way to do it. So this is just to have everything that, I mean, my users can use. So so then I wanted to tell you we have essentially some tricks to how to do the optimizations. Okay, we use the class information, but I think you use the tables as classes, so like there is not much difference there. And what we try to do, we try to remove certain constraints. So for us, the symmetric constraint is totally useless because, I mean, you can, if you know that Anna and Bob are friends as much as Bob and Anna are friends, you can just substitute. You choose one of the two that you like the most, let's say the one which is first in lexicographic order, and then you substitute everywhere the same thing. So in this case, if you had a grounded rule like this, like Bob votes Republicans, and if Bob votes Republicans and he's friends with Anna, then Bob is more likely to vote Republicans. No, Anna is more likely. Okay, I confused it. I mean, you can substitute, you can remove one of the two grounded predicates. You just use one of the two grounded predicates. They're symmetric, they're the same. You don't need to have two. So that's kind of trivial. So we cut some things there in the grounding. Then we were doing a lot of these tricks. So another trick we were doing is that sometimes you have functional constraints. Let's say, for example, you have a constraint that the person can have only one mother, and they have to have one mother, let's say. So let's assume that you know that Carla is Bob's mother, and you're, let's say, 0.9 sure. So then you can, like the constraint will be that the only other person in the world who can be the mother, let's say Anna, has to be the mother only 0.1. I mean, it has to sum up. So we were doing all these tricks. So if you can already find out things, you just assign the numbers. You don't need to do a minimization to find these things, right? So we were removing all the constraints which were easy to solve. You look, everyone looks a bit puzzled, but it's really tricks. So then we were trying to do something else with the functional constraints, so partial functional constraints. So in this case, you wanted to say that something is smaller than a certain number. And so if you, in IDMM, you can do it in a very easy way. You can do it in the consensus node itself. You don't need to have a subproblem which tells you this has to be smaller than that. And so we tried to essentially condense all the bounds, bound the variables to the smallest interval possible, and push it into the nodes so that we don't have to do a kind of trivial problem which says this has to be smaller, but you just can do it inside the consensus node. This is our kind of, yeah, tricks, as I said. And then other tricks were, obviously, you don't ground, you don't even need to do stuff. It's always true or it's always false. Why would you even consider it? So we cut that out. And so this was, we were reducing the grounding, and we have some experiments on how much it reduces the grounding from one of our synthetic data sets, but it's relatively uninteresting.
Hey,
yeah?
Sara, can you just give an example what you mean of the rules that are always true or always false? I guess I don't see how you would know that a rule would be always true or always false unless you did ground it.
So you ground it, and then you ground it, and you see that if you put like, even if you put ones on the left side, so if you essentially try the bounds and you see that even if the best condition, it's always true, so it wouldn't change. I have to remember exactly
Oh, okay. So you do the grounding once. You're just saying that after you know that you've already established that that rule is always true, then you won't repeat grounding.
Yeah, so maybe I misspoke. I meant that I throw away the ones. It's not that I don't ground them. I have to ground them to know that they're always true or always false. But
Right.
then once I know, I throw them away. I don't
Okay.
do inference with them. I mean, they are
Right.
they're useless for minimization.
Okay. Thanks.
So then for inference, we were experimenting with global convergence detection and local convergence detection. So Hugh's algorithm has this local convergence detection, and we implemented that. But then we implemented also the global one. So apparently, in signal collect can be implemented relatively efficiently because it turns out it's like a map reduce. So you have this graph, and they are sending messages, and you try to see if they have converged or not. And you can either try to see if they have converged on a local level, and parts of the things converge, or you can see if it has converged like by checking everything from a centralized global convergence checker. And so for us, at least, and in the experiments we found out, the global convergence detection was more precise because the local is an approximation. And so it was actually able to stop sooner. We were a bit surprised by this, that it was able to stop some steps sooner than the local one. So that was strange for us.
And did you find this over multiple data sets, or
No, we
this
just
was
used
particularly the voter
the
one?
voter dataset. Yeah. So also because we were, we sort of, we tried this, and then we sort of thought that maybe the local convergence was that we didn't implement it correctly, or that we compared also with other things, and we were not sure. So we decided that the global convergence detection was the sure one. So we decided to stick to that. So, but also for GraphLab implementation and our implementation with global convergence detection, and the other one with local convergence detection, GraphLab with local convergence detection runs much more steps. So, and the solution, like we compute the solution quality. So we try to see, we essentially compute, we are minimizing a function, right? So we just compute the function, and we allow a certain tolerance for certain constraints to be broken. And the solution we get is more similar to the one we get with, so we have an estimate of the correct ones, and ours is more similar than the one with local convergence detection. So we were guessing that maybe the local convergence detection makes some parts of the graph converge, and other parts of the graph, they have to work much more. So we actually, that's an interesting question for you guys more than us.
Yeah, so Steve or Hugh, do you have any thoughts relative to, I mean, it doesn't even have to be the distributed implementation, but this local versus global bit? So,
hey, sorry, we're just expecting to get unmuted. I would have to give this a little more thought. So, Sarah, can you just elaborate a little bit more? Maybe try saying it a different way. There was something I just didn't get about the distinction, because the way I think of our implementation currently, like UMD and UCSC's implementation, is a global convergence check. Is that using the right? Do you agree with that? Or are we using the language the same way?
So the one from Hugh on GraphLab uses a local convergence. It does. I mean, we can.
Oh, sorry.
The code seems to do that. It sends more messages. There are some specialized messages that it sends for this purpose. So okay. As I understand it as local convergence.
Okay. Yeah. So Lisa, my thoughts are just that global convergence checking is definitely nice. So let's. It's cool that Sarah's doing it. My recollection of Hugh's work, and you can chime in, is that local convergence checking was basically a concession to pragmatism.
Okay, I mean, that's fine. I was kind of curious whether it was a specific thing of the distributed implementation or not.
Yeah.
So, and also, you guys probably didn't hear the previous question. I was also curious about whether it's specific to the voter data at all. But anyways, Hugh, it sounds like you have something to say.
Yeah, I just drop out and just reconnect. I think the local convergence is some technique we proposed in the big data paper. At that time, it's more convenient to implement a local convergence in a graph lab setting because to do a global convergence, basically you need to have a global data gathering, which is pretty communication-wise, it's very costly. So in theory, the global convergence is more rigid, so it will converge faster than the local convergence, which is expected.
Okay.
And the global convergence is textbook technique. So we are customized it to implement a local convergence for distributed setting. And the global convergence and the local convergence communication side effect will be faded if the communication layer is very fast. So in Sara's experiment, they're using infinite band. So basically, that is super fast. So the savings from the communication will fade it out, and the global convergence will be more efficient in this setting.
Okay, good. Thanks.
Okay, so as we mentioned, for us, in our setting, it was faster than global convergence. In general, one thing we found also, which was very interesting, was that, convergence has an overhead, right? So we wanted to configure the convergence detection step so that you don't have to do it every step. You can actually, it's for apparently several cases, the stuff you're doing every iteration is faster than trying to understand if you have converged. So what we did is we let it run for a few iterations, let's say it ran 20 iterations on its own, and then we check the convergence every 20 iterations. So that was kind of the trade-off we found for our experiments between the extra steps and the overhead. But it obviously depends on the problem. And then what we tried to do, we implemented a lazy consensus optimization. And lazy means that we were trying not to send the same message twice, but to make it kind of work with Lagrangian multipliers being updated and etc. What we actually did is that we send the message. If it's the same message, you can send it twice if the internal state of the node has changed enough. So we have a threshold above which, if the internal state has changed enough, we send the node. And we have no theoretical demonstration, and actually I would be very happy if somebody would help me with that this is exactly equivalent or a good approximation of the normal ADMM. So that's allows us to save some messaging. By the way, it doesn't save so much. Apparently it saves like 30% of the messages, so it's relatively small. But still, no, 30% is not nothing. So, and so we use as mentioned, we use the voter social network. So there are these 4 data sets. I don't know if everybody is aware, but just to remind you, there are 4 data sets. They go from 550 to 2 million voters. And there are 7 rules, and you're trying to infer what do people vote based on the social network. And so this is the experiments we found. So we ran it on a cluster. It had like apparently maybe a similar setup to what you have. So we had like nodes with 128 gigs of RAM, and this is essentially the execution time. And we call ACO Hugh solution because we didn't. So that's the name of the algorithm, and we didn't find a better way to say, PSL on GraphLab, or we didn't know how to call it, so we call it ACO. And our implementation has has a few times less execution time. So I think it's a compounding of being signal collect, being faster. If you work with the person who develops the graph processing system, he can tell you exactly how to do stuff, so everything was more efficient. So we had some tricks to make it efficient for signal collect itself. And plus we have this lazy implementation of ADMM, I think also helped. And the convergence step being every 20 steps instead of having it every step was also helping. So everything together, it was faster.
So I have some question on the experiment mode for this.
Mm-hmm.
Like, I can understand some of the techniques you used will have some performance gain, but the 2 orders of magnitude performance gain is a little bit too much. Just thinking about the smallest data set you have here, and basically ACO is just an ADM implementation on GraphLab, and considering it's a smaller data set and a Lely inference won't saving too much, it's a 2 orders of magnitude saving comes from computation or communication. Does not. It's hard to explain here, right?
But it's not 2 orders. It's not like 1 order of magnitude. If you look at especially the last one, it's almost 1,000, and ACO is like about 6,000. So it's not 2 orders. Plus this specific graph is on 1,000 iterations, and on 1,000 iteration, I think that the global convergence actually stops around 300 iterations or something like that, and ACO actually doesn't stop the local one. The local one would continue, so we cut it at 1,000. So it's mostly because of that. It's because it doesn't converge. So it's also that influences. But on the other, so I have we can discuss this in depth if the other people don't seem super interested. But in general, if you want, we can discuss it in depth. So on the other iterations, not this one is specific, then it should be more similar. But I don't think it's 2 orders of magnitude.
Probably we can talk more in person, but
Yes, sounds like a good idea.
this gap seems to me is too much, because either.
So I think it would be good to have some of this discussion now, especially to the extent that we can understand certain aspects of whether convergence, local versus global convergence, grounding, kind of teasing those out, or other potential aspects. So why don't we have some of that discussion, but then you can also take some of that, because I don't know when you're going to be in person anyways.
It depends how much you want to see the causality thing. So that's the question. In any case, so we can have some discussion. So regarding to the grounding, actually this problem doesn't have the symmetric. So all of the tricks I show, I think that the grounding ones, they don't apply to this. By the way, this is already grounded. I also forgot that. So this one doesn't have any problem with the grounding. There's no grounding here.
Okay.
So that's easier. So grounding is not there.
Because we know that's an issue for many others.
Plus, I mean, this is an older version of what you did. So I would be curious. I know that you and Steve are working on a newer version of ADMM. So I would be curious maybe to try it with that or something like that.
Okay, and yeah, probably we can talk about it later.
Okay. Okay, so so I will just fastly talk about this. So I have a collaboration with someone in Amsterdam who's working on causal discovery. So we were trying to see if we can use PSL, and in particular FoxPSL, to do the causal discovery. And we still haven't understood if it's a good idea or not. So we can do it, but we don't know if it's better than the others. So this is something we have to discuss. And what is causal discovery? Causal discovery is that you have some variables. You know that certain variables are independent, and you want to understand which of the variables causes each other. So there are some algorithms which are from the 90s. One is called PC, one is fast causal inference called FCI, and some are based on logic. So you can write some logic rules, and you can say if something is independent of something, then maybe something causes something else. So I will show the rules to implement it, so that's easier to discuss. So using logic apparently helps for latent variables, helps when you have some data which are partially overlapping, like different experiments and they are partially overlapping, and it helps when you want to add some background knowledge. So this is much more difficult to do outside of the logic-based algorithms. But the problem is that, so logic usually cannot handle conflicts, right? Normal logic, not PSL. So what happens is that you test, the two things are independent, and you find out that your test tells you that with a certain p-value, they are most probably independent, but there is a very weak dependence. So you make a mistake, essentially. Your input is noisy. And then all this wonderful construction of these wonderful rules, everything falls out, and you find nothing useful. So we were searching for ways on how to handle the fact that they are noisy input. And my co-author, he thought of using MLNs, and so since we were there, I said, no, let's try to do it in PSL. So one other possible solution that you can use is answer set programming, which is some kind of logic-based programming, which allows some, you allow a lot of possible words, and then you can define certain constraints on the kind of weak constraints on the possible words, and you can define which one is the one that you prefer. So I'm sure probably in the paper of Steve, there is some kind of discussion that says that they are probably very similar. So the max works out and stuff like that. So what we did is we took some rules which were already there. We didn't invent the rules. We took some rules from a logic-based algorithm for find causal discovery, and then we implemented it in PSL. And then we added some weights to these independent tests. So it looks very vague, so I'll just go to the rules. So this one maybe make more sense. So this is an example of a program you can write. Let's assume you have some variables. You have the lowercase letters are the variables. You have, variables. You have the individuals in your word, U, W, X, and Y. And let's assume you have certain predicates. And one predicate is that something is independent of something else if you condition on a set of variables. And so this is one of the things we were adding to PSL. So we started, since we had this use case, we started adding certain things to PSL, and one was these sets. So in this case, you have, X is independent of epsilon on a base conditioning on a set, and we can have a minimum and a maximum cardinality for the set. So we have that you can condition on the empty set, or you can condition up to sets up to cardinality 3. Then you can have, so you look puzzled, so you can ask. Okay, so sorry if it's too small. So you have the independence predicate, and then you have the causes predicate. And the causes just means that X causes epsilon, as you can imagine. Then you have some very simple rules for consistency. One is that if X is independent of epsilon given Z, then also epsilon is independent of X given Z. It's similar to symmetry. Then you have some rules on how the causal relationships work. So causal relationships are irreflexive. So X cannot cause itself. And if X causes epsilon, then epsilon cannot cause X. So it's acyclic. So that's one of the assumptions. And then there is also the transitivity relations. So these are just...
Is there anything... So a question, in many of these causal discovery algorithms, they explicitly make some assumptions about what the confounders could be and what the space of confounders is. And so part of the reason I was looking puzzled is it's interesting that you're directly representing the logic of independence and causes in PSL.
Yeah.
Is a different way than I had been thinking of it initially. But can you also talk about that in this language? So saying something about, and there may be a confounder or not, or something that captures the faithfulness constraints that are typical. Are those typical in the logic-based ones too?
So so we assume that there is causal faithfulness. So we assume we have faithfulness and certain other causal sufficiency and some other assumptions. But for example, we don't model latent variables, but there could be latent variables. So I can show you an example. So what causal people usually do, they have these very simple examples with Y structures. And so if you know certain independencies, you cannot know, like there are some latent variables, but you can allow, so what you can answer is, I don't know. So I will try to show the next, I will try to show you the next rules, and let's see if they make sense, then we can discuss. So one simple rule is that if X and epsilon are independent, conditioning on nothing, so on their own, if they're dependent, but then you add Z, and they become independent. Then Z has to be the answer store, so it has to cause either X or Y. So this is very similar. So like this is essentially Bayesian network concepts of this separation. They are encoded in rules in logic. So this is the simple one. Then you can have the slightly less simple version. So you have if X and Y they were dependent when you have were conditioning on set W. But then when you condition on the set W and also Z, then they become independent. And in this case, this kind of notation is the union. So we added the notation of union of sets. So if this happens, so essentially Z is the first thing that makes X and Y independent. Then Z has to cause X or cause Y or cause something in the set W. And cause something in the set W, we wrote it in this with this syntactic sugar, which is there exists one thing in a set, and that thing for that thing Z causes W1, so that thing. So it's some kind of iterator if you think about programming languages. And this exists means that you unroll it to a disjunction. People seem very confused. So yeah.
You're saying that there exists an element in W?
Yes.
Which causes
yeah.
that.
So saying that,
So
yeah.
How are you iterating them?
So what happens is that saying that there exists an element in W such that Z causes that element, you can always say that you have, the W is, I don't say, like ABC. It's the same as saying, cause, yeah, exactly. So I just unroll it in disjunctions. So that's what happens.
But in general, the set of rules are some standard version of Perl's or Spirtes or.
So no, because Spirtes and so they didn't write it in first order logic. They wrote it. They had special algorithms, and they used their algorithms, so they are not in logic. But
since then,
yeah,
people have.
Exactly. People have developed first order. Okay, this is not first order logic. They say they have developed first order logic, but then there is this stuff which is like more second order logic. So people have claimed that they have done a logic representation of those algorithms, which is sound and complete with respect to what those algorithms find. So they are equivalent. You can show some equivalence. So there is a lot. These rules are from a paper which claims that the things that you find out, they're equivalent to what you would find with Spirtes and PC algorithms.
That was
and
the
stuff.
reference you had a couple of slides.
Yeah. So if you are interested, I can show you the reference.
But does that assume Boolean logic instead of creative logic?
Oh yeah.
Because that assumes Boolean logic, not creative logic.
Yeah, that one assumes Boolean logic. So actually, I can once I finish the rules, we can discuss that. That's one of the questions we were thinking about. So okay. This is one of the rules. I think I just showed the other rules, how they look. It's just one other rule, I think. So this one is the faithfulness assumption is that if X and Y are independent, they don't cause each other because they're independent. And then we had some essentially, well, I don't know how much you're interested in. This is essentially like the complementary of the other rule. It's saying that if X and Y, they are independent, given W. But then you add a certain Z, and they suddenly become dependent. Then Z is not causing anything. It's something which doesn't cause anything because you added it, and then they become dependent. You add it to the conditioning set, and they become dependent. Well, so essentially, this was just to show that we had to add certain iterators. This is a for each iterator. So for each means that you have to do an end, right? So exist, it's an OR, and for each is an end. And this was problematic because you cannot have ends on the right side, so you cannot do this, it's not convex. So we essentially just unroll it and rewrote the rule and put everything separately. So, well, maybe I'll go to, to that question there. This is a rule we are debating whether it has sense, but it has, so it was interesting because it uses some subsets of Z. So that's interesting for me as kind of from the logic perspective, if you can model the concept of having a set and then you have subsets of the set. And so that was interesting for me, but I can just go to the question. So the problem was we didn't know how to encode what we wanted to encode. So our inputs are independence tests. X and Y are independent, X and Y are independent given Z. So we have two ways to encode it. The one on the left is with Lukasiewicz logic. But then you get, if you put like probabilities into Lukasiewicz logic as facts, you don't get what you expect, right?
Yeah,
Exactly.
it won't work.
Exactly. So what we did is the second trial, we don't put facts. We have just a problem with all rules, and we put the probabilities on the rules.
So for the rule weights?
Yes, the weights become the probability. And we have that all the other, so we have a lot of these rules which say how the word should be, like things, if the things are independent, then things should cause each other. And we assume that those are constraints, those have infinite weight. And these rules, which say if X and Y are independent, these rules are soft. That's how we encoded it.
So how do you map from probabilities to weights?
So there is a way we will use some previous work on how to do this weighting. So apparently people tried 3 different ways. So one is you can put everything constant and see what happens. One is you can say that dependencies, I'm pretty sure that dependencies are correct. So dependencies have infinite weights and independencies have a low weight. So that's another thing that people have tried. And the third one is they did some complex thing that I can show you the paper. I don't know how they did it, but they managed to convert p-values into scores.
So can I clarify something?
Yes.
Okay. So when you had represented them as facts, and then you said that the truth value of these certain ground terms are, the scores from the t-tests or the p-values, right? The independence tests. On the right side, the rules that you have, X and U and so on, those are still like entities from your data set, or I guess they're sort of their ground terms, right? They're still fully grounded rules.
Mm-hmm. Yeah.
Is that right?
Yeah. So
okay.
Yes.
So all you're saying now is that the outputs, the p-values, instead of being truth values in PSL, they're going to be rule weights. So it's just like now basically it's saying that like for the first one, that X and U are conditioned on nothing. They're not independent, and that the truth value for that ground term is just going to be 1. But the rule weight is.
Yeah.
Is that right?
Yeah. So there is a way to convert p-values to probabilities of how much you think that a certain independence relationship holds. So there is some previous work we will use to decide the scores and the weights. So, but the problem is, so you're correct.
Okay.
My only problem we had was whether to use facts, rules, because facts, they more represent the vagueness, so the fuzziness, and the rules, they more represent the probabilities. If we use the facts, then we would have the Lukasiewicz operators combine these kind of probabilities, and they would turn out to be results which are highly like they are not expected. They do different stuff, right? They are used for different things. They shouldn't be probabilities, the fact. That's as far as I know.
Okay, thank you.
If you're sending messages, we don't hear you. We cannot see you. We don't know what's going on. Speak up. Okay, good. Okay, so everybody's puzzled, but the good part is that I'm finished. So, well, so essentially, it's if you're puzzled, it's probably because I was not very good at explaining it, because we just started working on it. I'm also very much a newbie in causality, so it seems very simple, but in practice, it's very confusing. That's what I learned up to now in a few months. And I think for me and essentially more my original group, which is on knowledge representation, the interesting part was having a problem that requires some extensions to the logic. So I don't think I ever found, in the wild, a problem which uses sets as variables, as that you have to have sets or that you need iterations over sets. I don't think you guys either, right? I mean, you use PSL for everything and you didn't find it, right? Exactly. So why would you find it? So this is one of the peculiar problems. So and it uses this kind of thing. So you could do it without sets, but then you would need to essentially write a predicate for all the possible cardinalities.
Yeah.
So that you can do it, but it becomes very difficult. And now I'm binding the sets to a certain minimum and maximum cardinality, but I'm allowing also to not bound it. So in that case, that's simply not possible to write it in normal logic.
Yeah.
So in first order logic. So this is some kind of bastard second order logic. So bastardized, yeah. It's not very clean.
And I do think, I think there's a variety of backgrounds in the group in terms of how much they know even about the basic independence and dependence reasoning in graphical models. So some people know it very well, they TA'd it and so on. Other people probably maybe is a little bit fresh. And then on top of that, knowing the pieces with the causal modeling. But I think this is a good starting point for then having some more tutorials. I know there was at least one tutorial where I wasn't at, and I don't know how much you guys covered of these things. But one question I had, maybe I have this flipped. I always end up having these things flipped, but it sounds like your assumption is the dependence statements are pretty good that you get, but the independence statements are the ones that you question. I always thought it was the other way around, that when you, first off, that these independence tests are notoriously noisy.
Yeah.
But I thought the error went the opposite way. I thought it was that they often would say things that were dependent when they actually weren't dependent, and that it was more that you do all these tests and nothing ever ends up actually being independent. So do I have that mixed up, or is there
So I think that there are several problems. So you have the false positive, the false negative, etc. Right?
Yeah.
So, but apparently, the guy I'm working with, which is doing 7 years this, so I trust him. He said that it's really difficult to distinguish between a weak dependency and an independency. And then like your P-score, if you put the threshold, if you sort of accept many things, you put the threshold too low. If you put the threshold too low, then you accept, and then you are more strict, right?
Yeah.
So if you're more strict, you will start thinking that stuff is always a bit dependent, and as you said, then you'll find out that nothing is independent in your model. So it's very difficult to find the correct p-value, because if you put it low, then everything is dependent. If you put it high, a lot of things which are not independent are suddenly dependent. So it's the problem with the tests. So one of the assumptions is you cannot solve the tests, take the tests as they are. We try to put a lot of things together and aggregate them and hope that, by aggregating them, we solve these inconsistencies. So that was the idea. We're using, people in the domain, they use, there's some Bayesian testing and there is some t-test. So you can use both, but apparently...
But still, they're making these assumptions.
Yeah, so there's still a lot of errors. So
yeah.
And if we make the tests good, then we don't have a job. So we should use the the simple ones.
Yeah. So we have a question.
Okay.
And the question was, we were talking that you were trying to do this a little bit for the yeast genome, right? Trying to infer causal regulatory relationships in the yeast genes.
Yeah.
Is there, as it stands right now, you have a whole bunch of experimental data, I assume, and probably on the full genome and multiple different types of experiments and stuff. For each data set, do you compute an independence test and try and you get some scores, or do you aggregate over all your data and then do that kind of thing?
At the moment, we have 2 datasets, but we are not. So what happens is that we have funding for doing that. That's why we're doing that. Otherwise, we would be doing other things. Have funding and datasets for doing that. And the golden data is available because people do, like, there is interest in finding these gene regulatory networks. So what happens is that we have 2 datasets, and we would like to integrate them, but at the moment we can use only one at a time because it's not clear, because they are 10 years apart, and it's not clear if integrating them it's a good idea. So that's a work that another PhD student is working on. So for now, for me, it's only one dataset, so I don't have the problem. But in the future, I think it's a good question. So I don't know yet.
Okay. Yeah, my question was just about whether it makes sense to try and integrate the information from both. But yeah, that's good.
But the problem is that you don't know if there are some. Apparently, they have some measurement on the cell, and the cell can be in a different cell cycle for whatever that means. And apparently, the data set somehow they are dishomogeneous in some of these things. So there are some latent variables that we don't know. Let's say some content or something. And so not as easy, luckily. We were hoping that, yeah.
Okay,
so for this thing, we were trying to do it with PSL, but another thing we tried was if we can convert it to an integer linear programming problem. So what we do is we essentially do the grounding with PSL, and then we translate it to an integer linear program. So that means that we get out only decisions if yes or no, it causes or not causes. Otherwise, you would get it causes 0.6 or something like that. And well, so the problem at the moment, our biggest problem is that when I do the grounding, things kind of a bit explode. So not for these small datasets, but for like even our competitor on 10 variables, they cannot go on. So it's that field. It's the field of 7 variables most. So
yeah, that's interesting. The complete difference at the symposium. There were the causal model guys that had 5 variables.
Yeah.
Thing at 3 variables, and then the data people and the stats people that had, really big data sets and quite different worlds. So it was interesting to watch. All right. Well, any Links East questions, comments?
Yeah, I actually had this one question about the first part of the talk. Sara, did you run any experiments where you just compared a single core instance of FoxPSL versus the regular ADMM?
So actually, no, we didn't. I think it probably is a good idea. So we didn't because I think that if we run a single core FoxPSL and we compare it with the centralized version of ADMM, it will obviously be faster, the centralized version, because it's you have a lot of overhead to set up the things on the single core. So I don't think it's in general, and I'm not sure. I'm a newbie in 20 fields. One is also the distributed graph processing, and I suppose that usually if you run it on one node, it doesn't have sense, right?
Well, it seems like you implemented all of these optimizations in the grounding. That it seems like if there were an implementation that got rid of the parallelization overhead stuff, it seems like you could get some improvement in performance even on a single core.
Okay, I can try that, but I think the centralized version will be faster. So we can bet.
Yeah, my hunch is that the optimizations that Sara discussed, it's about making a more compact equivalent Hinge loss MRF. And I think if you were there you would have the benefits no matter what. But I think if you took Hinge loss MRF, like if you gave them both the same Hinge loss MRF, I suspect they would be very, very similar, just because it's running the same basic ADMM updates for the subtypes. Okay. Yeah. The optimization totally makes sense, or not the numeric optimization.
Right. Yeah. No, I mean that's what I was.
Yeah, I mean, I guess on that note, and this is not just a FoxPSL question; it's a generic question. To what extent do you think that the grounding is taking a lot of? I mean, so making a more compact ADMM problem is great, but my intuition is in a lot of our problems, the grounding is what dominates the time, and it sounds like you still have to do the grounding, and then you have to do additional work to post-process the grounding. So to what extent do you think you're actually saving time?
You mean that the post-process, like when I do the grounding, I post-process stuff, but it saves me some time because I can decide. So, well, when I do the grounding, I have also to, since it's an object-oriented thing, I have to create the objects. I can decide not to create the objects, so I can do some post-processing. I think it saves some time. I don't know.
I see. So the post-processing is integrated with creating the objects for the ADMM optimization. So it shouldn't really be taking any additional time.
For me, no. But I suspect that. So I'm doing it. So we're doing it, and also the other ADMM version is doing it from. So we're doing it. Okay. We're not doing it using a database. That's the problem for me. And I suspect that if I use Staffy or any other thing that uses a database to do the grounding, or any other kind of more optimized grounding for MLN, I think it would be better. Because I suspect that, I'm quite confident that MLN and PSL have the same grounding mechanism. So I'm sure they have some other grounding systems that we can use.
Right. I mean, I guess that makes sense that if you had, I guess what makes sense is, well, actually, it's not. I think even in PSL, right? You'll run the query, you'll get a bunch of groundings, and then at the time you're turning those groundings into an ADMM problem, you could exclude some things, and that would be, if we did this in our current PSL implementation, it would be fine because it would be the same thing. The post-processing would kind of happen, would be integrated into creating the ADMM problems. So I think that's the way you're doing it is probably completely valid. And then the question of throwing out these constraints, what does it bias? I imagine the constraints are actually where a lot of the convergence time is spent. And maybe this is the difference between Hugh's version and your version, is that for a symmetric constraint, even being off a little bit could cause many more iterations, whereas you can dispense with it the way you're doing the bounds and converge much more quickly. I don't know if that made sense to other people.
Intuitively, I think you're right, Jay. Yeah, that's my. That makes sense. I buy that.
I think that chart Sara made is after grounding and comparing purely the optimization problem and the same problem.
Exactly, it's after grounding, so it doesn't change with the comparison. With
and also,
no, it's after grounding in that, but it includes your optimizations for symmetric and functional constraints, right?
Because there are no symmetric constraints or functional constraints in the problem, so it doesn't.
Right, but Hugh's. So you're running Hugh's code with the same groundings.
Right.
I also have some other experiments on my own benchmark, but I didn't show them.
Wait. So actually, this is something I didn't understand. So in Hugh's GraphLab implementation, you're throwing out the symmetric and functional constraints, and you're doing the bounds trick for his version too?
No. It's much more easy. We use the voter dataset. The voter dataset has a set of rules. In that set of rules, there is no symmetric, there is no functional. I think there is partial functional, if I remember correctly. But it cannot be. It's not one of the trivial ones, so I cannot optimize it. Essentially, in general, in any case, I use the things which are already grounded.
So you're just treating these other unknowns in the symmetric constraints as observed.
Can you explain?
Hey, you're back.
Who?
Is it Alan?
Okay. So my question is, you did a comparison with GraphLab.
Yes.
Did you run Hugh's GraphLab code?
Yes.
And when you did that, so you have optimizations to remove symmetric and functional constraints. So did you remove the symmetric and functional constraints when you ran Hugh's code?
She's already said twice that the problem didn't have any symmetric or functional constraints in it.
I thought it was the voter data set.
Yeah. It doesn't. I mean, okay, look, I take the voter data set. I don't know if you have other versions, but the ones I have, with the 7 rules I have, it doesn't have the constraints. In any case, it's not a problem because you sent me already the grounded data. So I already have the grounded data. We run on the same grounding, so it's the same problem from ADMM perspective. So and luckily in that case, I don't even do the grounding, so I cannot show any improvement in the grounding. I can show it in another data set if you're interested.
I see. So none of the results you presented use your grounding optimizations.
No. Yes, you're right.
Okay. That was confusing. Sorry.
Sorry.
And also on Ben's question, actually, some of the techniques like lazy inference we also had in the GraphLab implementation. Basically, key idea is skipping some of the values skipping some of the x having the same value, so you don't send it over. This only makes sense in the distributed setting where you want to save the communication. And for a single machine, comparison will be, well, you're getting part of the array, not whole array, so it won't make a lot of improvement in a single machine.
Okay.
Yeah.
But I would be curious to like if there is a if it's not too difficult for me, I would be curious to see if any of the optimizations I can make, I can port them to the centralized version. Although I do think that the distributed version is the future, you know. So I do believe that it's better to have a better distributed version than the better centralized. I don't know.
It's okay.
Yeah, no, it didn't make sense. Okay, it's good.
No, it makes tons of sense. So we need a distributed version.
You have a distributed version. But I'm I'm totally agnostic now. I'm using Signal Collect, but since I mentioned that the Signal Collect guy went to industry and we lost him, so I was interested in the ADMM implementation that Hugh and Steve were working on. Nice. Life. This is the answer to you.
So Sarah said she's really interested in your distributed ADMM implementation, Hugh and Steve.
Oh, okay. It's a question. Yeah, currently we're playing with the ADMM optimization layers. There's no connection with PSL front end yet.
Oh, okay.
The distributed grounding seems to us is an interesting problem.
Yeah.
But there's not much work on the distributed grounding yet.
So, but did you do something on distributed grounding by chance or not yet?
Not yet.
Okay, that's interesting. That's interesting to know. Yeah. So because I was mentioning that I would like to do stuff with distributed databases, but it still wouldn't be distributed with databases, but it still wouldn't be distributed, right? If you do the joins, the toughy stuff is still centralized, as far as I understand.
Right, and also the grounding you did in your work in FoxPSL is still, it's also on the Signal and Collect?
So the grounding is not on Signal Collect.
Okay, it's a single machine scale-up problem.
Yeah, exactly. So we have the same, we didn't solve this problem. We don't have distributed grounding. So that's one of the problems for us as well.
Okay, I see.
So, but I was curious about your implementation of ADMM. If you were doing it, because I didn't understand if you were doing it in Spark or something like that, because I was curious about trying to essentially implement the algorithms I have in Spark or in another different graph processing system.
No, we're just build it from scratch.
Oh, okay. That's difficult for me. Okay, great.
Okay.
Since we have in there, can we figure out the time for you to talk on next Friday?
Okay. So we have a talk tomorrow at 1 Pacific on PSL, and then next week we want to have Hugh's talk. And Jimmy said, Hugh, you're traveling on next Friday. Is that right?
Yeah, I'm flying to Seattle next Friday night. So better start the meeting earlier so I can head to the airport.
Okay.
Yeah.
So if we had it at 11 a.m. Pacific, is that early enough or probably not, right?
Yeah, it's early enough. I think I can do it.
Are you sure?
Yeah, it's the flight is 6 p.m. so.
Okay.
6 p.m. East time.
From where though?
From Baltimore, BWI.
Yes.
Yeah, because 11 o'clock would be 2 o'clock there. So
Yeah, right. So we can finish around before 4, then I can still catch up the flight.
You're crazy.
I mean, if we finish at 4, it's already 2 hours for the meeting, right? So.
Yeah, but it's Friday afternoon traffic. I guess you drive fast. but you're definitely not taking the bus or anything like that, right?
I drive by myself, so it's
Okay.
no problem, I think.
Okay. Okay, so we'll do it at 11 next Friday.
And before we go, Lisa, I just wanted to clarify for us, the group. You said we're going to have a talk, and by that you mean we're going to have a chat, right? Like, so what I'm really hoping is that people are going to give me their feedback on what's already been sent out, and so I can certainly take people through it, but it will be most helpful if people come having read as much as they can of the draft.
Oh, yeah, yeah. So, sorry, I didn't mean...
I have slides.
No.
It is very much going to be structured around giving feedback. It may have some components that are real time. So I think some of it may be, okay, we'll focus on a section, and then we may take a few minutes to, like, say, someone will say, oh, this is confusing, and then give people a chance, like, everybody go, like, read that part and kind of brainstorm like that.
Yeah.
And if you have other suggestions of how to make it work better, but we'll do this as a first pass at trying to do something like this. We've never done something with this bigger group trying to do a distributed feedback. So it's an experiment. Experiments sometimes fail. But, I mean, if you think it would be better to have
QCRs?
Yeah, I want QCRs.
Danya was reminiscing about how great they were the other day.
I think that sounds very good, Lisa. That sounds good to me. If anybody else has any other suggestions.
Half of the people don't even know what you're talking about. But the best thing that I came up with that I never had at University of Maryland was the BYOP.
Bring your own paper.
Yes.
What is P?
P is paper.
Okay, I got it.
So for folks that are not in the know, when I run these reading group things, trying to have some way of giving feedback on papers, we make everybody do QCRs. So they have to have a question about the paper, a comment about the paper, and a research idea from the paper. So everybody likes the QCRs. I need to trademark that. That will be my claim to fame someday. Okay, so a question would be, maybe what we can do is we can do this in real time where we have some Google Doc. So bring your laptops where in the Google Doc we can put comments about certain sections and everybody can kind of add them at once so that, you know, we don't have to go around the room and like, oh, you had a typo here or something like that. We can have a place to collect those pieces, and then we'll see how it evolves. Okay?
Okay, sounds good.
All right. Yes, but no talk. Yes.
Yeah.
We'll mainly be listening or typing or something.
Yeah. Okay, thanks, everybody. Thanks, Sarah.
Thank
Right.
you. Ciao.
Thanks, Sarah.
Bye. Thanks, Sarah. Enjoy the rest of your Santa Cruz time.
Thanks.
Okay, so what I had suggested for those available is that we could have